In this video, we're going to talk about a very useful form of the Fourier transform, the discrete Fourier transform. So Fourier series and the Fourier transform are very useful for finding the oscillations that make up any particular function. But, of course, real life does not have smooth functions. Well, and real physics in particular does not just smooth functions, it's made up of data. And so we need to think about how to use data instead of smooth functions in doing Fourier transforms. So I'll draw some sample data here. I've got a bunch of data points that maybe look something like an oscillation here. And I'm just showing one period of the oscillation of the data. And so here a function, f of x, was really just represented as data, as a bunch of data points. In particular, we have n total points here, and the points are spaced by some spacing, let's call it delta x, apart. For our purposes, we're going to be assuming that delta x is a constant so that we have equal spacing. Otherwise, things get really messy really quickly, and that's a whole nother topic. So for example, if we let delta x equal to 2 and big N be 10, then we would have data points for some function at the values f at 0, f at 2, f at 4, so on and so forth until we get to f at 18. For us and for our purposes, we're going to be labeling this in a different way. And so we're going to label this as f sub 0 for the 0th point, f sub 1, f sub 2, up to f sub n minus 1. So that's how we're going to be labeling our data points. In general, you could write this as f sub r, and that's equal to the function evaluated at r times delta x. And that's going to be the labeling of our points in our data set. Note that r here is an integer, and it's running between 0 and n minus 1. Okay, so let's go back to the usual Fourier transform and recall how that works. So the Fourier transform was defined as the function is square root of 1 over 2 pi, negative infinity to infinity, integral f hat of p e to the I px dx. For the discrete Fourier transform, we're going to turn this into a sum instead of an integral. So f sub r is a sum from n equal to 0 to n minus 1, f hat of n divided by big N, e to the minus 2 pi over big N, which would be an I n times r. A couple things to notice here. The index little r is replacing the x dependence that we had before. We turned the integral here into a sum, as usual when you go from continuous to discrete. The amplitude here, or the transform, this f hat, there's a factor of 1 over big N, and that's just a convention that you don't need to worry too much about. And then up here, the index n, little n, is now an integer, and it's taking the role of what we used to have as frequency in the Fourier transform. Okay, so that's the discrete Fourier transform. Let's think about how we can interpret this. What is the interpretation of the Fourier transform? Usually, with the Fourier transform, we think of f hat of p as the amplitude of some particular angular frequency p. What happens in the discrete Fourier transform? Well, it works similarly. Now, f hat of sub n is a set of n amplitudes, so there's n of them, and they correspond to different angular frequencies. But now those angular frequencies is given by expression 2 pi over big N delta x times the little value n, for whatever that little value n is. Note here that n is an integer, just a number, but p is the corresponding angular frequency. And that's really important when we're going to be interpreting our results. The calculation won't be a problem, but interpreting we'll have to think about. Okay, so we're almost there, but we need to figure out how do we find the amplitudes, these f hat sub n's. Again, let's go back to the Fourier transform. So in the continuous Fourier transform, we found f hat at p is equal to 1 over the square root of 2 pi, integral from negative infinity to infinity, the function f of x, e to the minus I px dx. So let's just turn that into a discrete version to get the discrete Fourier transform. And by the way, we're just going to call that dft for short from now on. Okay, so f hat sub n is the sum from r equals 0 to n minus 1, f sub r, e to the minus I 2 pi over big N, little n times r, where the f sub r are the values of the functions. Note there's no 1 over n here, as there was with the forward version of the Fourier transform. Okay, so just one thing to note, that the discrete Fourier transform, as we compute it here, doesn't care at all about the spacing of our points, the delta x in particular. It doesn't show up in the formula at all. So this expression for the discrete Fourier transform just spits out n minus 1 values, or numbers, given by a set f hat sub n. And we have to do something with that in order to interpret it. So in particular, we're going to have to convert the integers, these n's, to frequencies, or angular frequencies, if we really want to make sense out of what we're getting from this calculation. And that's what we're going to do in future videos.